thank you very much for the invitation to present today. I'm going to talk to you today about the work that we're doing on auxetic materials and obviously the relevance we hope to biomedical devices. Well, we all know what happens when you pull a foam. It stretches, it gets longer, and it gets thinner, okay? So that's what happens, and we expect that happens with just about every material that we can think about. In fact, what we play with, though, are materials that when you pull them, they actually get fatter rather than thinner, okay? And that's a mechanism there. I'm not going to go into detail today as to how we do that, but as I say, the effect is that they get fatter when you pull them or thinner when you compress them. And these are called auxetic materials, and they have what is known as a negative Poisson's ratio, okay? This is quite an old slide now, but there are quite a few materials now known or have been developed with the effect from the nanoscale up to the genuinely macro scale, and covering all the classes from metals, ceramics, polymers, and composites. There are naturally occurring biomaterials known to have the effect. Certain forms of bone and a number of forms of skin, and so there could be implications there in synthetic biomaterial developments. The motivation for us as a team and for the other groups around the world looking at these materials now is that obviously there's an interest in the property itself. It's counterintuitive, there's high volume change, so there's potential applications there. But also, there's a number of other properties that are enhanced by having a negative value of the Poisson's ratio. I've listed a few there, but there are quite a lot of others as well. So double curvature, energy absorption, indentation resistance, and fracture toughness have all been experimentally demonstrated to be enhanced in some way by having this negative Poisson's ratio effect. And this is a simple example. So on the left-hand side here, I've got a normal honeycomb. It's a hexagonal honeycomb. It's positive Poisson's ratio, and if you want to form it into a dome shape, it's very difficult. You bend it and it saddles up. If you go to the auxetic equivalent, which has this bow tie structure again, when you bend it now, it forms a very nice dome shape. And that's because the radii, the two principal radii of curvature are related to the Poisson's ratio, and the sign here obviously determines the sense of the two radii. Okay. So one of the earliest materials that was found to have the effect is PTFE, and we've done work looking at developing other microporous polymers with this effect. And a very early example then was to think about where the effect might be useful in applications that use PTFE. So arterial prostheses, this is an example of a blood vessel. The wall here is in this case, it's got a positive Poisson's ratio, so where the pulse of blood is going through, it's under radial expansion or circumferential expansion, and so the thickness of the wall decreases, okay, and could potentially rupture and split. If it's got the auxetic property, now the pulse is circumferentially stretching again, and because it's got a negative Poisson's ratio, therefore the thickness of the wall increases to prevent potential rupture. Another early example that you see in the patent literature is that of a dilator. So this is a device that's got a finger and thumb mechanism, a bit like a syringe, and when you push that in, it basically extends this end member that is auxetic PTFE. Because it's auxetic, it expands and therefore can open up the vessel within which you've inserted this device. There have been developments on this, but the basic advantages are that you don't need an inflation medium that you would do in a normal balloon catheter. So you don't have to worry about inflation pressures or leakage of the inflation medium. It's very easy to control the expansion, and we can make a series of dilators of different dimensions, if you like, to give you controlled distension. And there's been other patents on using alternative materials. So ultra-high molecular polyethylene gives you the potential to have stronger devices with larger diameter inner lumens for the same outer diameter of the device, and a number of processing benefits as well. There are examples of origami stents that have been in the literature. So again, you can insert them in their compact form and then deploy them into the extended form. And again, there are a number of patents on different types of liners and things that you might use for stents and how you might achieve playing around with the geometry to get that. I was asked to bring us up to date, if you like, on where we are with auxetic material, so I'm very pleased to pull together a slide from a number of slides that were presented by Brunel's very own Tony Hansen last week at the international conference that we hosted in Bolton, Auxetics. This is again on sort of smart drug-eluting auxetic stents, so he's looking at this rotating squares mechanism to get the auxetic effect. So you can see that as you pull it, it expands. He's rolling that into a tube and using fusion welding to make the tubular device. He's incorporating a shape memory alloy material to give you large strain dilation mechanisms, and he's coating the polymer with the rotated square material with a polymer, a dissolvable polymer with a chemotherapy agent in there. So genuinely, I think multifunctional device there. We can look at the ability of the auxetic to anchor into a surrounding material in some way. So this is an example. You've got an anchor surrounded by a biomaterial in this case. If it's a normal anchor material, then if it's under tension, it will contract and you'll get failure at the interface. If it's an auxetic anchor, it will expand and lock into the material, so you should get improved anchorability. Well, we made the world's first auxetic fibres a few years ago, and we're able to show in single fibre pull-out tests that this indeed works. So this is a single fibre pull-out test on auxetic and non-auxetic PP fibre samples, and you can see that the auxetic sample can withstand twice the maximum force, and the area under the curve tells us 3 times the energy is required to pull that out. So this anchorability effect, and therefore potential in sutures and ligament devices and so forth is there. We can incorporate our fibres now into fabrics. So this is an example of a knitted fabric with auxetic monofilaments and a woven fabric. Last week, a.alderson from Bolton reported on incorporating auxetic fibres into non-woven fabrics at the conference. Another area we've looked at is the effect on the change of porosity in a porous auxetic material. So this is a normal non-auxetic honeycomb. We've got a particle block in it here, and if you want to clean that membrane by pulling it mechanically to open up the pores, it's not possible. The pores close up in one direction as they open up in the other. If, on the other hand, in a moment we go to the auxetic case, now when you pull, the pores open up in all directions, that particle goes through, so you can either clean the filter or you can release the active ingredient or whatever it might be that you're trying to get to go through that membrane. Okay, and we showed that was a very simple set of tests there, and we've done that in foams and also in simulations of molecular devices. So we could combine our fibre and our fibre technology and the ability to put it into fabrics with this entrapment, this entrapment to release scheme or controlled release scheme into a smart bandage. So here's a bandage. It's made out of auxetic fibres. Within the fibre micropores, we've got an active ingredient in there, okay? And as the wound swells, what will that do? It stretches the bandage, it stretches the fibres, the fibre micropores open up, they release the active ingredient onto the wound, okay? Once the wound swelling goes down, the fibres relax back, the pores close up, and you switch off the release of the drug. Okay? Any secondary inflammation would reactivate that bandage to restart the drug release. So we believe that's a genuinely smart concept, and we're quite a number of these components of that concept we've proved now. We can make auxetic fabrics out of normal fibres. Okay, so we don't have to put auxetic fibres in there. So we're designing now the auxetic effect at the fabric structure level rather than the fibre level. And this is an example of one that we made. There are a number of other groups around the world now also producing fabrics using different approaches. And so we could combine that fabric with a coloured substrate to give us, again, a mechanism for making a sort of colour change material there by using 2 components. Okay. Another thing that we've done recently is make auxetic materials where the properties and the structure vary in space, so gradient auxetics. The way you would make a normal auxetic foam, a thermoplastic foam, would be you'd start with a conventional foam, you put it into a smaller container, you heat it to its softening point. That allows the structure to relax into this new structure that will give you the auxetic effect, and then when you cool it below the softening point, it freezes the structure into that new structure. So that's how you would normally do it. We've adapted that process to give us non-uniform compression regimes so that we can vary the amount of compression during the conversion process and therefore change the structure
in space. Okay, and this is the tomography work that we do with Phil Withers' group in Manchester. So this is this structure is characteristic of the normal foam that we start with, and as you go down the thickness, we get into this more contortuous, twisted topology that we know is the auxetic structure. And one of the things that you get then, once you can vary the structures, you vary the elastic properties, and therefore we now have developed a simple shape change material that changes shape just on simple uniaxial stretching. Okay, so we're now thinking, where can we use that in devices? And we've coined the term piezomorphic materials, and that is now published online for these. So these are shape change materials for simple stretching. So we can now look at a second generation multifunctional type of bandage application. We've now got not just auxetic fibres or auxetic foam as the component hosting the active ingredient, but we've also got an auxetic fabric structure. Okay, and we can, at the fabric scale, have colour patches put in there, so we can the nurse who's applying the bandage can tell when it's got the right tension, it's changed to the right colour. Yeah. And now, when the wound swells, not only do we activate release of the drug, but we have more control over that release if it's a gradient structure. By not only does the pore size vary with the amount of stretch, but it also varies with the position in the bandage structure itself. And of course, if we've got the auxetic effect at the fabric structure scale, the pores we open up, so we get enhanced breathability to again accelerate the wound healing process. Okay, and again, it all switches off once the wound heals. You've probably all seen this guy recently. Another area that we're looking at or starting to consider is prosthetic liners. What we think in terms of the liner the auxetic layer will give us is, you've seen the double curvature. Well, the stump is a doubly curved part of the body. So we think that will help in that. You'll see shortly that we get impact support response in auxetics. There's a number of energy absorption studies that have shown enhancements for auxetics. So we think we can get a lighter device for equivalent energy absorption response. The high volume change we think will be useful in compensating for variations in stump volume during the day or in highly active situations. We think we'll get the improved fixation that you saw in the anchorability study earlier on. And again, this issue of breathability as the material expands and contracts. And we believe we'll get the optimal solution by going to the gradient system. Another area that is attracting some attention is in hip implant devices. If we think about the cup liner materials, you know, one of the main sources of failure for total hip replacement devices is aseptic loosening due to the generation of debris as the liner and the head cause wear on each other. So the debris then gets into the body, it causes interactions, which then ends up with loosening of the stem device. So if we could reduce the wear of the liner in some way, then we might be able to lengthen the lifetime of the device in some way. And the main causes of wear in these materials are adhesive wear, which is related to indentation resistance, and abrasive wear, which is related to fracture toughness. So if we can increase those two properties, we should be able to increase the wear properties of these materials. Well, the fracture toughness is related to the Poisson's ratio by this expression, and Poisson's ratio for isotropic materials goes down to -1. That should be +0.5, not -0.5. Sorry, +0.5. That's the range of Poisson's ratio, and you can see for this expression, it's a Poisson's ratio squared term, so you get enhancements when you're in the -0.5 to -1 regime. Okay, so we think, again, fracture toughness should be enhanced, and it's been demonstrated in a number of materials. So we should get improved wear properties because of that. Indentation response, again, that's the mathematical expression. You've seen a benefit in the -0.5 to -1 Poisson's ratio regime. Hand waving, what's happening is if that's a normal material and you've got an impactor, under the indenter, it's under compression, and therefore it's positive Poisson's ratio, so the material tries to expand away. Yeah. Whereas for the auxetic case, it's under compression, so negative Poisson's ratio, it wants to contract and densify underneath the indent. So you get the local densification where you need it. So that could be a mattress or what have you. And that's some data from a few years ago now that's showing that the hardness of the material increases as the Poisson's ratio goes more negative. Okay. We've looked also now at the stem of these devices. One of the problems you get with stem materials where the modulus of the stem is greater than that of the bone is that the load is transferred to the distal end, if you like, and so you get densification of the skeleton at the distal end, and around the proximal region you get stress shielding. It's basically the bone is unloaded, it becomes weak and what have you. So that you want to avoid, mesh stems have recently been reported where they get a better match to the mechanical properties of the bone. We're saying, okay, if you can get a mesh stem, we can look at altering the properties even further, not just to match the modulus, but we can play around with the Poisson's ratio. So this is a solid stem, this is a conventional mesh stem, and these are two auxetic mesh stems. And we've modelled those using finite element modelling, and you can see here for the mesh stem cases, the conventional one shows a build-up of stress in the bone at the distal end, whereas the build-up of stress is much reduced when you use the auxetic implants. So we believe that by careful design of the mesh geometry to give you the auxetic effect, we can reduce the detrimental stress shielding in hip implant devices. And in fact, that's one of a number of potential applications that or benefits we can see for these devices. We could also put in there an inner screw mechanism to give us a deployability function. I'm not talking large strain deployability here, but enough to tighten a device once it starts to loosen in some way without having to completely replace the device. So we'd have to think about it a bit, obviously, about the engineering that would require, but our initial studies show that should be feasible. Okay. So we think we can come up with a device where we've got this deployability function. We require, if it's deployable and starts in a lower volume state, therefore we require to take less bone out to actually receive the implant, which should be a benefit, but more natural material existing, reduced time to prepare the bone to receive the implant, and faster rehabilitation time. We can optimally fit the stem by applying the right amount of deployability. And that's pretty much it. The porous part gives us a new bone ingrowth. We've mentioned the reduced stress shielding effect, and the energy absorption properties, which should also be a benefit. So finally, I'd like to acknowledge the team, past and present, who have been involved with various aspects of this work, and the funding sources, and that just sums up what we do in Auxetics at Bolton. Thank you.
Any questions? I think there's a question. Was there? Oh, sorry. While people are thinking, can people use these auxetic materials for energy storage? Is that something that people are looking at?
Probably on the quiet, yes. Yeah.
Okay.
We can design materials at the right scale for energy storage applications.
Right.
Yeah. And we've published some preliminary studies on
Okay.
that. Yeah.
Okay, thank you. Other questions? Okay, well, thanks very much.